Impedance.
Hello people, we are back once again, and today we'll be talking about impedance. Impedance. So now let's check on the slide and look at the definition for impedance.
The opposition to current flow in AC circuits owing to the presence of combination of resistive, inductive, and capacitive elements. Opposition due to inductance is called the inductive reactance, and opposition due to capacitance is called the capacitive reactance. And this opposition is known as impedance.
Okay, so with impedance, from the definition, we are seeing these three elements. So we are seeing the inductive, the capacitive, and the resistive. So now we are seeing the inductors, the capacitors, and the resistors that will oppose the flow of current in an AC circuit. So now the opposition of the flow of current in an AC circuit caused by any of these three elements is what we call the impedance. And impedance is represented by Z. So in our normal circuit diagrams, the opposition to the flow of current was resistance. That is caused by the resistor. But in an AC circuit diagram particularly, the opposition to the flow of current by the inductors, the capacitors, and by the resistors, together we call it the impedance. And that is represented by Z. So now the inductors will produce the inductive reactance, which is most of the time represented by XL, because the inductor is L. So now the capacitive also produce the capacitive reactance, which is also represented by most of the time XC. And the resistive will produce X reactance, which is represented by capital R. So now when these all reactants oppose the flow of current in an AC circuit, then we have what we call the impedance. So now let's consider all of them and see the formulas of what we can use. So now let's first take in a resistor. So in a resistor, so if you take a resistor for instance, resistor is the symbol is this. So this is the resistor. So we want to check the effect of current and voltages across a resistor, the effect of current and voltages across an inductor, and the current and voltages across a capacitor. So you want to check. So in a resistor, there is current coming to the resistor, and there is this voltage. Now, what do you know here? You realize that from Ohm's law, V is equal to IR. So if from Ohm's law, V is equal to IR, then the current that is coming will obviously be V on R. So if you let V, which is equal to, that is a sinusoidal quantity, which is equal to Vm sine the angular frequency times t. If you let V equals to this, then what can we say about this? The only thing we can say is that if I is equal to V on R, and this V is equal to Vm sine omega t on R. So if you're having this and this is equal to that, then we can say this I is simply what? Equal to In, because from here, Vm over R will give you In. So if Vm over I will give you In, then I is equal to In sine of omega t. In sine of omega t. But there is one thing you're supposed to also note here. So what you're supposed to note here is that for the current and the voltage across in a resistor, the relationship between them is that you have to know that the current and the voltage are always in phase. So the current and the voltage across that resistor, they are always in phase. There is no phase angle between them. None of them is lagging or leading each other. So the current and the voltage are always are always in phase. So none of them is leading each other. So if current has this phase like this, voltage will also have this phase like this. So there is no phase angle, or the phase angle is equal to what? Is equal to 0. That is when we are talking about in a resistor. Now let's look at the relationship between current and voltage in an inductor. The relationship between current and voltage in an inductor. Okay, so in an inductor, we want to look at when current is passing through an inductor. So this is the symbol for an inductor, L. We want to know the voltage relationship and current relationship when they pass through an inductor. But you should know that the reactance here, because from Ohm's law, you know that V is equal to IR. But the reactance here in an inductor is what? Is the inductive reactance. So therefore, we get our VL, that's our voltage across an inductor, to what? The current IL, but you know that always the current will be the same, and our inductive reactance. So this is something you're supposed to also take note over here. Okay. Now what happens is that V is L di over dt. V is L di over dt. Okay. So if V is L di over dt, then we have a relation that if you let I is equal to Im sine omega t. If I is equal to Im sine omega t, then our V now becomes L. So from the relation here, we can find V, that is the I on the t across. So V is equal to the inductor multiplying what? The derivative of what? Of the current with respect to time. So if that is the case, then the I on the t, that is here. So if you find the I on the t here, what are you getting? Anytime you find sine omega t or sine of anything, we are getting Im omega or Im omega cos of omega t. So Im omega cos of the omega t. So therefore the V finally becomes L. Now the I is this times Im omega cos of omega t. Okay. So now this is what we're having now. So now you can finally see that then V is equal to the omega L Im cos of the omega t. The omega L Im cos of the omega t. So now, anytime you want to change cos to sine, you have to add a fixed angle of 90 degrees. So from here, we can have V is equal to the omega L Il sine of omega t plus 90 degrees. So if you are changing the cos here to sine value, you have to add 90 degrees to it. Okay. As a fixed angle. So therefore, finally, what are you having? You're having our V to be equal to Vm. To be equal to Vm sine omega t plus what? 90 degrees. So the whole of this function is giving us what we call the Vm. So now what can we derive from this place over here? What we can see from here is that XL is always equal to omega times L. So XL is always equal to what? Omega times L. So now, if XL is equal to omega times L, then we can have our V omega L Im to should equal to our Vm. So therefore, our XL Im should equal to what? Our Vm. So this is our peak voltage and this was our peak current. So if I have the peak current times the inductive reactance, you are getting what? The peak voltage. So that is why this correlation became what? Vm. Now what can we conclude here? What we can conclude here is that for inductors, anytime you see an inductor, current and voltage relationship in an inductor is that current lags voltage by 90 degrees. So this is something you shouldn't forget. When we talk about the resistors, we said the current and the voltage, they are always in phase. But in terms of inductors, the relationship between the current and the voltage, current lags voltage by 90 degrees. So it's something you are supposed to take note here. And that is here. So by 90 degrees. So anytime you have to find the relationship, current will lag the voltage by 90. So now if you write the voltage, if the voltage is in phase like this, then current. So that is current lagging the voltage by 90. So the voltage is here, then current will be here. So the same way, if you put current here, then voltage will be here. So now, this is the same way. So if voltage is in phase like this, current will be here, lagging it by 90. But if you put current here, voltage here, then it will be here, lagging it by 90. So now this one will be like the voltage across the VL, and this one will be the current. Please do get it. So let's look at the last one, which is the inductor. Capacitors. Alright, so the relationship in capacitors. Okay, so now we have some current that is coming, and this is the symbol for a capacitor. They have to be the same. So this is a capacitor. You have some amount of voltage across the capacitor. Okay. Now there's something you're also supposed to note over here that, as I said, from V is equal to R, the resistance in the capacitor, or the resistance in the capacitor is known as the capacitive reactance. So therefore, here you can find the voltage across the capacitor as IC, I said the current is always the same, times the capacitive reactance. I get it. V is equal to IR, but the resistance here is for the capacitive reactance. Okay, so now from here, what we can say is that the current that is coming will be equal to what? The capacitance times the derivative of the current with respect to time. The current that is coming is equal to the capacitance times the derivative of the current with respect to time. So now I is equal to C dI on dt. C dI on dt. So from this relation, when we say let Vm equal to Vm sine omega t. When Vm is equal to Vm sine omega t, then we can have that is sorry. It should just be the V on the T. It should be the V on the T. Yeah, because the current across here becomes the capacitance times the derivative of the voltage across the capacitor. So now, if it's the V on the T, then that's the V on the T here. So now the V is this. So we are finding the derivative of this parameter against time. So we get Vm omega cos omega t. So we are differentiating the sign. Okay. So now if you differentiate the sign, that is simple. If you have something like sine 5x, and you have to find maybe y is equal to sine 5x, and you have to find the y dx. It's simple. You have to multiply the value here by differentiating sign, you get cos. So cos what? 5x. So this is something you should know from your basic secondary school. Okay. So now from here, what we get is that therefore the I now becomes the C, which is this C. Now the V over the T is what? Vm omega cos omega T. So if you have this, what you can get from here is that our I can now be equal to the omega C V and now if you want to change the cos back to sine, then you can just sine omega t, you have to add your 90 degrees as we did for the inductor. Okay, so we having this, then finally you can see that the current that will flow here will be equal to WC Vm sine omega t plus 90. But if you know, this is a peak. This is a peak voltage. A peak voltage. So you can simply have I is equal to Im. I is equal to Im sine omega t plus 90 degrees. This is always a sinusoidal quantity. So if this is the case, then Im is equal to times the peak voltage. But a relationship you are supposed to also know here is that something you are supposed to know here is that for capacitors, current always leads voltage by 90. For capacitors, current leads voltage by 90 degrees. No matter what is happening, for capacitors, current is always leading voltage by 90 degrees. So now, if you have current here for a capacitor, then voltage will be here. So in other words, you can say the voltage is lagging the current. So current is always leading voltage by 90 in capacitor. So therefore, the SC, that is the capacitive reactance, is always equal to 1 over the omega times C. 1 over the omega over C. I get, so if you get this one, so this one, then that will be. So from here, how do you find the Vm? Vm is simple 1 over omega C times the Im. So if you want to find V, so from here V is equal to Ohm's law. If you want to find the capacitive reactance, the I is the same as the Im. One of the capacitive reactance Xc, which is equal to what? 1 over omega C. So it's something you're supposed to take note. But what we did for the inductance, you have what? S is equal to what? Sorry, XL is equal to what? The omega L. But for the capacitive reactance, we're having 1 over what? The omega C. So these two things, you have to put it in your head, and it will help us solve other questions. This brings us to the end of this video, and let's meet in the other class to know that the series connections between inductor and the resistor, the capacitor and the resistor, and when we connect the three of them. Bye.